Hello, my dear students. Welcome to my YouTube channel, Shiv Academy of Mathematics. So, in this video, I am going to prove the Fubini's theorem. It is a very important theorem in measure theory. So, before starting this theorem, we need some definitions, some results, some theorems which we have to use in the Fubini's theorem. So, first of all, we will see those definitions, those results, or those theorems. So, in this, if you look at the first definition on your screen, it is the product measure. So, first of all, we will define the product measure. So, in the definition of product measure, if you see, we have taken two fixed measure spaces, xs mu and y sigma nu. So, we have taken two fixed measure spaces, x s mu and y sigma nu. This is x s mu and y sigma nu. So, we define this S cross sigma. S cross sigma is the set of all A cross B, where A belongs to S and B belongs to this sigma. So, this is what a product semi-ring of subsets of X cross Y. So, basically, if we talk about this semi-ring in measure theory, so the collection of sets which is closed under intersection, that is known as the semi-ring. Otherwise, you know about the semi group. So just like we define the semi group, we can define the semi ring on the same line. That if S plus, because in a ring we need two binary compositions, addition and multiplication. So to define the semi ring, S plus must be abelian group, and that S dot with the S dot, that is also a semi group. Then we can say that is the semi ring. So but if we talk about this measure theory, it is the collection of sets which is closed under intersection. So that is what known as the semi ring. So but our concern is about to prove this Fubini theorem, and to prove this Fubini theorem we need the definition of this product measure. So this S cross sigma, we are taking the product semi-ring of subsets of X cross Y, and we define the set function. Set function is basically what the set function, if you know, it is the function whose domain of definition is a class of sets. So if you look at this definition, mu cross nu, we have taken this domain as S cross sigma, and the range is 0 to infinity by mu cross nu A cross B equal to, it is mu A nu B, mu A into nu B, for each A cross B belong to S cross sigma. So here what we have taken, this A cross B belongs to this S cross sigma, A cross B belongs to S cross sigma. So this set function, just I told you that the set function whose domain of definition is a class of sets, that is what known as the set function. I have discussed in one of my videos about this set function, so you can watch in that video about the set function. So this set function, this mu cross nu, is a measure on the product semi-ring S cross sigma, and this is what called the product measure of mu and nu. This is what known as the product measure of mu and nu. Sorry. So in the definition of product measure, few things are important. First of all, this S cross sigma, which you have taken the set of all A cross B, for which A belongs to this S, B belongs to this sigma. Then we have defined mu cross nu from S cross sigma to 0 infinity by this mu cross nu A cross B equal to mu A into nu B. And then we are saying that this set function is a measure on the product semi-ring S cross sigma. And what is this known as the product? This is what known as the product measure of mu and nu. So this was the first definition which we have to make use in the Fubini's theorem. So next we come to the first theorem which we have to use in the Fubini's theorem proof. In this theorem, what we are going to prove? We are going to prove that this mu cross nu is a measure. Mu cross nu is a measure, because in this definition we have taken this as a measure. So we are going to prove the set function mu cross nu from S cross sigma to 0 infinity, defined by mu cross nu in A cross B equal to mu A into nu B. For each A cross B belonging to S cross sigma is a measure. So this we have to prove this is a measure. So you know very well that when you have to prove any measure, we have to prove two things, that mu cross nu phi equal to 0, the null set is having measure 0, and the second, mu cross nu is subadditive. These two things we have to prove. First of all, we will prove that mu cross nu phi equal to 0 and mu cross nu is subadditive. But you know, because xs mu and y sigma nu are measure spaces, so these mu and nu are measures, s and sigma are sigma algebras. So you know very well that a null set has measure 0. That's why we can say that it is clear that mu cross nu phi equal to 0. So no need to prove more things, because these mu and nu both are measures. Because this mu cross nu phi will be that mu phi into nu phi. It will be mu phi dot nu phi, and both are having value 0, so it is 0 into 0 is equal to 0. So we will get that mu cross nu phi is equal to 0. And to prove this 2, that is mu cross nu is subadditive. So what we do, we take A cross B belongs to S cross sigma, and An cross Bn be a sequence of mutually disjoint sets of S cross sigma, such that this An cross Bn, it is a sequence of mutually disjoint sets of S cross sigma, such that A cross B is equal to union An cross Bn. So we have taken this A cross B belongs to S cross sigma, and this An cross Bn, it is a sequence of mutually disjoint sets of S cross sigma, such that A cross B is the union of this mutually disjoint sets union An cross Bn. So dear students, now because we have to prove, because the second thing was what we have to prove, that mu cross nu is subadditive. So what we prove, that's why we are writing here, it is enough to prove that mu A dot nu B equal to summation n equal to 1 to infinity mu An dot into nu Bn, which we have taken here, because we have to prove that is a subadditive. So we are starting from here. If either mu of A equal to 0 or what you say nu of B equal to 0, then one holds clearly, because in that case both sides will turn into 0. So let us assume that this mu A is non-zero and nu B is also non-zero. Mu A is also non-zero, nu B is also non-zero. Now you know very well about a function that is known as the characteristic function chi A cross B. That is because we have taken this. Look at here, A cross B is what? It is the union of An cross Bn. So when we take this chi of A cross B, chi of A cross B equal to sigma n equal to 1 to infinity chi of An cross Bn. I have written a definition of characteristic function chi Ax equal to two values 0 and 1. If x does not belong to A, then answer is 0. X belongs to A, then answer is 1. So that's why we are writing here chi A cross B equal to sigma n equal to 1 to infinity chi of An cross Bn. So we see that chi Ax into chi By. So what we get? Sigma n equal to 1 to infinity An chi Anx into chi Bny holds for all x and y. So these two terms will get separate, chi an and chi bn. In the next part, what we are doing, we are fixing an element y belonging to this set B. That means to say, we are applying the definition of y belongs to B or y does not belong to B. If y does not belong to B, then chi by is 0, and if y belongs to B, then chi by is 1. But you know very well that A cross B is the countable union of A n cross B n. That's why this chi bn in the right side, it is chi bn y. So chi bn y is nothing, it is 0 if y does not belong to Bn, and 1 if y belongs to Bn. So we are what doing here, we are applying the definition of characteristic function, just I discussed at the top of this page. So if we apply this result, so what we get here, chi ax, because what we are saying that chi b and y equal to 0 for all y does not belong to Bn, and it is y for y belong to Bn. So this chi ax is what is sigma belonging to k, chi aix. Look at this. Because if this y does not belong to Bn, all those terms will become 0. Only we are having those terms in which this y belongs to Bn. And in all those cases, this value of chi Bn is nothing, it is 1. That's why we are having only the chi x in the left side and sigma. This summation now also change from this n equal to 1 to infinity. Because if suppose y does not belong to B10, then we will not take n equal to 10. In that case, this value is 0 and the whole term will become 0. That's why what we are getting, chi ax equal to sigma I belonging to k, where I have taken this k is equal to summation, this set of I belong to n, y belongs to bi. And we are having left only this chi aix instead of this chi anx, because what I am saying, we are having only those terms in which this y belongs to Bn. Otherwise, all other terms remain 0. That's why we are having only this chi ax equal to summation I belongs to k, chi aix. And k is nothing, it is some set of all those I belong to n for which y belongs to bi. And because we have taken on the previous page that this collection is mutually disjoint collection, that's why we are writing from the same that this collection AI must be disjoint. This collection, observe that the collection AI belongs to this K must be disjoint, and thus what we are getting, mu A equal to mu of A is equal to summation I belong to K mu of AI holds. In that case, this measure of A will be the summation of all those I belong to K mu AI. And therefore, finally we have to show this result, mu A into mu B. So mu A we have taken here. Now come to that second part, mu B. So for that, what we are doing, we are multiplying mu A with this chi by. So it is mu A into chi by is equal to summation n equal to 1 to infinity mu an and chi bny. Because this A cross B was the union an cross Bn. That means to say we are having mu A, that's why it is mu an, and it is chi B, so it is chi bny. Because we have taken chi x into chi by equal to sigma chi nx into chi bny. That's why we are saying it holds for all y belong to I, because we are fixing y belong to B. That's why we are talking about y belong to y. And my dear students, we know if some term is having this measure an equal to 0. Suppose we are having one or two terms whose this mu measure is 0. So because this is an infinite series, so this sum doesn't affect if we remove 1, 2, 3, 4 terms. That's why we are writing a since a term with mu an equal to 0 does not alter the sum in 1 or 2, because one was which we have to prove. Look at this, mu into nu b equal to sigma mu n into nu bn. And the same thing what we are saying here in the 2. that since a term with mu an equal to 0 does not alter the sum in 1 or 2, we can assume that mu an not equal to 0 for all n. So here we are supposing that this mu of n is not equal to 0 for all n, or for all n. And one more thing, suppose we are having both A and B finite measures, both are having finite measures, then integrating term by term, we see that this one holds because it is sigma n equal to 1 to infinity mu n nu bn. So this chi bn will convert into this nu bn. And if we are having on the other side A and B having finite measures, so what we get, this sigma n equal to infinity mu n into nu n equal to infinity. It is the right side of 1, because either A or B is having infinite measure, and A is the countable union of these A's, B is the countable union of these B's. So because this means to say this RHS is infinite and the LHS in 1 is mu into nu b. So what we are saying that if this last sum, the last sum means to say the sum in 2 is finite, then this mu a chi by, then mu a chi by, because we know very well that definite integral has limits, so it is an integral function, means to say we are getting the value finite. But here we are saying that this sum is infinite. That's why it is not possible. Why? Because we are saying that both either A or B has infinite measure. So this is not possible. Because if it defines the integral function, that means to say the sum we are having get finite value. That means to say, in this case, one holds with both sides infinite, because I told you it was the right side of 1 and the LHS was mu into nu b. So both sides will be infinite. That means to say our result, which either we were taking this 1 or we were taking 2, so this countable subadditive property also holds. And that's why, my dear students, what we can say that this mu cross nu, the set function is a measure. This mu cross nu is a measure. So you understand this theorem. In this we have proved that mu cross nu is a measure. Just like you know very well about the outer measure. So now we will denote by this mu cross nu star outer measure generated by the measure space x cross y, s cross sigma, mu cross nu on this x cross y. That means to say now we are talking about these product measures. And the notation for this outer measure is mu cross nu star. Mu cross nu star. This mu cross nu star is the outer measure. And generated by what? X cross y, s cross sigma, algebra, mu cross nu, the measures on this x cross y, So it is the notation. Just in measure theory we denote by m star the outer measure, or you can say mu star. Just I told in the starting of the video that we have to make use of some results, some theorems. I am taking those theorems without proof, which you have to make use in the Fubini's theorem. So in this sequence, the first theorem is what? If A contained in X and B contained in Y are measurable sets of finite measure. These two are measurable sets having finite measure. Then this mu cross nu star A cross B is equal to mu star A and nu star B. So it will become the product of these two outer measures. So I can upload the videos related to the proof of these two theorems also. But here I am taking just the results, that if A and B are two measurable sets of finite measure, then mu cross nu star A cross B is nothing, it is mu star A into nu star B. And second theorem which we have to use, if A is a mu measurable subset of X, And second one is B is a new measurable subset of this Y. Then A cross B is a mu cross new measurable subset of X cross Y. So my dear student, here A is mu measurable subset of X, B is new measurable subset of Y. Then this A cross B is mu cross new measurable subset of X cross Y. X cross Y. So next we will define sections, means to say X section and the Y section. I have taken an example also in this. So how we will define X section and the Y section? If A is a subset of X cross Y and X belongs to X, then X section of A is defined by A and we take in the suffix X. So when we are talking about the X section, in that case we will take the elements, all those elements of Y for which this pair XY belongs to A. This pair XY belongs to A. And clearly this X section is the subset of Y, because in this we are taking elements of Y, We will take all those elements, for which this XY pair belongs to A. Similarly, if Y belongs to Y, then the Y section by A is defined by AY equal to set of all those X belong to X for which XY belongs to A, it is the subset of X. So when we are taking AX, it is the subset of Y. When we are taking AY, it is the subset of X. Just like I have taken an example so that you can understand this X section and the Y section. Just like X I have taken 1, 2, Y I have taken 3, 4. So if we do the Cartesian product of X and Y, so we are having 1, 3, 1, 4, 2, 3, 2, 4. So I have taken this A because A is subset of X cross Y. So I have taken A as 1, 3 and 2, 3. A as 1, 3 and 2, 3. So AX is what? Because in AX we have to take Y belong to Y for which XY belongs to A. So this 3 is Y, that means to say AX is 3, which is the subset of Y. And AY is what? 1 and 2. The first elements in the pair, which is equal to same X. So in this way we can define the X section and the Y section of a subset. So next come to one more definition. In this definition, what we have taken, we will define the iterated integral, and we check that whenever it exists. So we have taken f from x cross y to r. It is the real valued function. Then the iterated integral, it will be double integral because we have taken the domain of f as x cross y. So it is the double integral f du dv is said to exist if fy, this is the cross section, y section, this is the y section. If fy is an integrable function over x for nu almost all y and the function gy equal to integral gy, what will be gy? Integral fy d mu equal to, so it will change into the single integral over x, because the ay, the y section was the subset of x. So that's why this gy is integral over x, fxy d mu x defines an integrable function over y, So next we are saying that if E is a mu cross new measurable subset of x cross y, if E is a mu cross new measurable subset of x cross y with this outer measure of E finite, because I have taken this outer measure of mu cross nu, then both the iterated integrals, first iterated integral is what? Double integral chi e d mu d nu, and double integral chi e d nu d mu exist, and the value of this double integral chi e d mu d nu is equal to double integral chi e d nu d mu equal to single integral chi e with respect to this mu cross nu. That's why we have taken here d mu cross nu. and this is what mu cross nu star e. In outer measure also you have read about the connection between the outer measure and the integral. So here, because we have taken the domain as x cross y, that's why we are connecting this mu outer measure with the double integral. That's why this mu cross nu star e is nothing, it is double integral chi e d mu d nu. And again we have taken some theory from the measure theory that since every mu cross nu step function is a linear combination of characteristic functions of mu cross nu measurable sets of finite measure. Because when we define this characteristic function, then step function, simple functions, so we are talking about the step function. Step function is nothing, it is a linear combination of characteristic functions. That's why we have written here, since every mu cross nu step function is a linear combination of characteristic functions of mu cross nu measurable sets of finite measure, it follows that if phi is a mu cross nu step function, if here phi is a mu cross nu step function, then both the iterated integrals, means to say which iterated integrals, phi d mu d nu and double integral phi d nu d mu exist, and moreover double integral of this phi d mu d nu is equal to double integral phi d nu d mu is nothing, it is a single integral phi d mu cross nu. I think that all such kind of results you have read in your measure theory, and the connection between the integral and the measures. So step function, this is the characteristic functions. So all those results we have taken in this product measure also. So I think there is nothing new, but only the new thing is what the product measure. So finally, let us come to the Fubini's theorem. By making use of all these definitions, results, theorems, or some more basic concepts of measure theory. So let us look at this Fubini's theorem. In the statement of Fubini's theorem is, we have given a function f from x cross y to r. It is a mu cross nu integrable function. Then what we have to show, both the iterated integrals exist. Just we have taken in the previous that we have defined two iterated integrals. Then we have to show these both iterated integrals exist, and next we have to prove double integral f d mu cross nu is equal to double integral f d mu d nu equal to double integral f d nu d mu. So we have to show that in this Fubini's theorem, the key point which we have to prove that both iterated integrals exist, and then we have to show these three integrals are equal. So in the proof, dear students, I have taken that without loss of generality, we can assume that this f is non-negative, holds for all x, and we choose a sequence phi n of step functions such that 0 less than equal to phi n xy, and it converts to this fxy. This converts to fxy, holds for all x and y. So we are assuming that this fxy is non-negative, and a sequence phi n of step functions. Step functions, I just told you, it is a linear combination of characteristic functions. So that's why we have taken the sequence in the form of phi n, and it is converging to this fxy, holds for all x and y. Holds for all x and y. So because we have to show that both the iterated integrals exist, so what do we do? We take this double integral x, first integral over x, then integral over y, phi n xy d nu y d mu x. So dear students, here one thing which you have to remember, we are integrating with respect to x as well as y. So because it is integral over y, so we have taken here d nu y, and then secondly we are integrating over x, so it is d mu x. So apply the definition, it is nothing, it is phi n d of mu cross nu, phi n d mu cross nu. In the definition we have taken. Again I am showing you this. Just like it is chi e d nu equal to chi e d mu cross nu, single integral. So, or what you can say, we have taken here, double integral phi d mu nu equal to integral or phi d mu cross nu. So, we are applying the same result, that this double integral will convert into the single integral, but it is or d mu cross nu, and because this phi n was converging to f, so it is converging to f d mu cross nu. F d mu cross nu, and because it is the integrable function, that's why it is less than infinity. So again we are making use of one more theorem, and that let E be a mu cross nu measurable subset of x cross y with mu cross E star mu cross nu star E less than infinity, that is finite. Then for mu almost all x, the set Ex, it is the x section, is a new measurable subset of y, and the function x to this nu star Ex defines an integral function over x is such that this mu cross nu star E is equal to, it is integral over x nu star Ex d of mu x. So which result we are applying? First what we are saying, it is the set Ex, which is new measurable subset of y, and the function we have taken x to this nu star Ex. Similarly, we can talk about the Ey. Ey is a mu measurable subset of x, and the function we have taken now y to mu star Ey. Just like in the previous, we have taken x to nu star Ex. Here we have taken y to mu star Ey. So it defines an integral function over y such that this mu cross nu star E equal to integral over y mu star Ey d of nu y. So we are applying it for each n, the function gnx equal to integral phi nx d mu equal to integral over y phi nx by d nu y, integral phi nx by d nu y. Because we have taken these two results, one over the x section and second over the y section. So that's why we are saying that this gnx equal to integral phi nx y d nu y, it defines an integral function over x, and this definitely what we can say that this gnx is convergent for mu almost all x, and we are applying after that one more theorem. It is the Levy's theorem. Levy's theorem is what that assume that a sequence fn of integral functions satisfies fn less than equal to fn plus 1 almost everywhere for all n, and limit integral fn dum is finite, then there exists an integrable function f such that fn converges to f almost everywhere. Almost everywhere, you know, the set of points where it fails to hold, is a set having measure 0. When we are saying that a property holds almost everywhere, the set of points where it fails to hold is a set of measure 0. So we are saying that this fn converges to f almost everywhere. So we apply this Levy's theorem. So according to that, because we were saying that this gnx is an integral function over x, that's why this gnx converges to an integrable function. That's why we have taken there exists a mu integrable function g from x to r such that gnx converges to gx almost everywhere holds. That is, just I told you the definition of almost everywhere, that is there exists a mu null subset of a of x. Null subset means to say the property where it fails to hold is a set having measure 0. That's why we are saying mu null subset. And this integral phi n x d nu converges to this gx, which is finite because we are saying it is integrable function. That's why we have taken it as less than infinity, holds for all x does not belong to A. For all x does not belong to A. But this, because we are saying this phi n x converges to fx, phi n x converges to fx, holds for each x. That's why we can say that this fx is new integrable function for all x does not belong to A. For all x does not belong to A. And that's why we can say that this gnx is nothing, it is the integral phi n x d nu, and it is integral over y phi n x by d nu y, which converts to this fx d nu over y, holds for all x does not belong to A. So here are lot of connections of definitions, theorems in this Fubini theorem. So you have to watch each and every result very carefully to prove this Fubini theorem. So this dnx converges to this integral fx d nu holds for all x does not belong to A. Now this one, we have taken this one, double integral phi n x by d nu y d mu x, it is finite. So what we are saying here, now 1 implies that the function x2, this fx d nu defines an integral function such that, now we are applying this result here in this part, because phi n is converging to f. That's why that will convert into f. So it will be f d mu cross nu equal to integral over x integral over y fx d nu d mu equal to double integral f d nu d mu. And similarly, my dear students, we can prove that this f d mu cross nu equal to f d mu d nu. And from this we can say that these three integrals are equal, and the integrals, iterated integrals also exist. So dear students, in this way we can prove the Fubini's theorem. So in the description link I will upload the PDF of all these definitions, the results, this Fubini theorem. And if you are having any doubt, then you can write it in the comment box. So you understand this Fubini theorem, and don't forget to subscribe our YouTube channel Shiv Academy of Mathematics for more updates, for more videos. So thank you. Have a nice day.